Hi, my name is Adrian Cidre, and in this tutorial we will build these two maps using R. So these maps are showcasing the pre-wildfire vegetation and moisture analysis of Tenerife. And this analysis is between the 15th of July of 2023 and the 15th of August of 2023, because this day started a wildfire in this area right here that burned around 15,000 hectares. So in this tutorial we will use a new R package called RSI, which makes us easy to retrieve Sentinel-2 data in R. So we will see how to retrieve this Sentinel-2 data and how to create these maps using the same package. So in this tutorial, as you can see, I'm not using RStudio, but the new IDE that was released a couple of days ago by Posit, the same company that developed RStudio, because they developed this Positron IDE, which is now in beta, so it can have some bugs, errors, and so on. But I think it's pretty cool, and we will see how it looks in this tutorial. So we will start with this tutorial and I will start loading the packages that we will use. As usual, I will use the pacman package, which has this pload function, which can be used to load the rest of the packages, and if any of them is not installed, it will install it. So I will run this line of code, and here we have the gisco r function that we will use to retrieve the study area, the patchwork package, and I will use it at the end to build the final visualization so we can assemble two plots. The SF package for simple features so we can manipulate vectorial data. This RSA package, which is the one that I want to show you in this tutorial, which is the one I will use to retrieve Sentinel-2 data. The Terra package for manipulating the raster data. tidyterra for using spat rasters in ggplot2, and finally the tidyverse. So we will start loading the data. And the data that we need for this tutorial is the study area that we want, which is in this case the Tenerife island, and the satellite image for the island. So first we will obtain the Tenerife boundaries, and to do so we will use this gisco-getNats function, and we will set the country to be Spain, the resolution to be 01, so this is the highest resolution, and the NATS level to be 3. So the NATS level will give us for Spain the province level. So I will print just this part of the code in the console and we will see how it looks. And here we have this simple feature collection with 59 features which correspond to each of the provinces. And here we will use this name Latin column to filter only Tenerife. And since this is in a geodetic coordinate reference system, and for this function we need projected coordinates, we need to transform it. And in this case, I'm using this EPCG code, which corresponds to the UTM coordinates for the Canary Islands. So I will execute all of this code, and after it's finished, I will print it in the console so we can see that everything went well. And here we have now a simple feature collection with only one feature corresponding to Tenerife. And we can generate a quick plot, so I will use the plot function for the geometry of Tenerife SF. And if I make this a little bit bigger, where is this? There we see that this is the island. So we can go to the next step, which is the satellite image. And for the satellite image, we will use this get Sentinel-2 imagery, and we have some arguments. The first one is the area of interest, which in this case it will be the Tenerife SF polygon that we got from the previous step. And then we have the start and the end dates. And for the start date, I chose the 15th of July of 2023. And the end date is the 15th of August of the 2023. And I choose these dates because the wildfire started this day, so I want to get an average of the vegetation index and moisture index of the month before the wildfire. And if I open the help of this function with F1, here we have the function. We see that we have this argument, the composite function. So all the images that fell between this range, they will be reduced to only one image where we will have the median. And then here in asset names, we have this argument here, and you see that it's using this function. And here I have this function, which I can print now in the console. And you see that this function gives us this result. And this is basically a character vector with these elements, but it's an special object of the RSI package, but this behaves like a character vector. So we can select the bands that we want from this image because we don't need to download all of them, so we can save us some time. And the ones that I want to get are the blue bands, so the number 2, the green, the red, so that's why I have here the band 2, 3, and 4. Then we need the near infrared, which is the 8th band, and the short infrared, which is this one right here. So that's why I have this vector, which I will execute, and I will print now in the console. And we see that now we have only these bands instead of having the 12 of them. So now I will execute this, but before I will load this TikTok package, so I can check how long does it take to run this function, because it will take a while. So I will use their TikTok, and now I will execute it, and when it's finished, I will come back and we will see how long does it takes. And finally, we have also this other argument, which is the output file name. And here I'm just saving it to the temporary directory with this name, sentinel.tif. So now I will pause the video and come back when it's downloaded. Alright, we are back now that the function has finished. And as you can see, it took 913 seconds, which is approximately 15 minutes. So now we have our image. But if I print this in the console, you will see that this is just a path. And it's a path to the image that we defined in this output file name. So since it's just the path, we need to read it with the Rust function. And here you see that I divided by the factor of 10,000. And this is because when the images are stored in the cloud, they are multiplied by this factor. So instead of storing floats, they are storing integers. So now when we apply this transformation, we get the digital values, which are between, as you see, approximately 0 to approximately, in this case, 2. And we can visualize the RGB image, so the true color image, using this plot RGB function from the Terra package. So I will execute it. So here I have the image that we downloaded. Here I need to specify the index of the RGB bands. So if I go back here, you see that the red is in this case is the third one. The green one is the second one, and the blue is the first one. So that's why we have to write 3, 2, 1. And then I'm scaling the values to be between 0 and 2. And I'm making here one stretch so we have nice values. Because otherwise this function would think that the maximum value is 255, and we would just see a black image, as you will see in a moment. So there we have it. As you see, it's very dark. And of course, if I delete this scale, is when the image will be completely dark. So that's why we need to add those two arguments. So we need to stretch the values and to scale it in a value of the values that we have here. So we can try also to see 1 or 0.3 is a value that I usually use for the Sentinel-2 images, and it's usually a good choice. So we see, and it looks like this. And the previous image that we had, it was pretty similar. Alright, so now we will prepare the data for calculating the spectral indexes. So the first thing that I want to do is to mask only the island, because I don't want the sea pixels. So we can use the mask function to mask this image only to to the SF object, which is the polygon of the island. So if I execute this, I can plot again the RGB so we can see what this function has done. So I will execute it again. And here we have it. So as you see, we eliminated the C. And this is because we use this polygon. And what we say with the mask is that the values that are outside the polygon, I want them to convert them to NA. So now we have this new image. And one thing that is really cool from this RSA package is that we have access to the awesome spectral indices database. So if I print this in the console, I will make these plots smaller and I will make this a bit bigger. You see that we have available 243 different indexes. And here we have the application domains, so they are classified by different domains. We can check how many are available. So I will use here application underscore domain and pipe this into the unique function. And you see that we have different indexes for vegetation, water, burn, soil, and so on. And here we have some URL, the date of addition of this index to the awesome indexes database in GitHub. Here we have the formula, the long name of the index. So I will print it again, spectral indices, and I will say glimpse so we can see it better. And here we have the date of addition, the formula that you can explore there, the long name. So here we have long names and the short names are just the first letters of them. Then we have also some reference and the platforms for which they can be calculated, because some indexes, maybe they have some bands that are not available in some of the images that we have, so they are not available for all of them. And in this case, we will use this spectral indices database and we will filter by the short name. So I will filter the NDMI and the NDVI. So if I print this, okay, I missed this S, we see that we are filtering these two indexes. So I will execute it again. So we make sure that we save it to this new table. And now we have these calculate indices from the same package, the RSI, where we specify the raster, so in this case the Tenerife spot raster, the indices table, so in the case that I put these spectral indices here, it will calculate the 243 indexes for this image. But that wouldn't be possible because the Sentinel-2 image is missing some bands that are necessary for some spectral indices. So before you need to filter out those that are not available for your particular case. And then here I need also to specify an output file name. Again, I'm storing it into the temporary directory. So I will execute this. This should be faster, but it looks that it will take a while. So I will pause the video again and come back when it's finished. Alright, so now it's finished. We can print this object in the console and we see again that we just have the path to the file. So we need to read it with the Rust function. So I will execute it. And now if I print it in the console, here we have our new spot raster with two bands and one band for each of the indexes. And now in this case, I will do a classification for the NDMI. So here we have values from approximately minus 0.6 to 0.6 approximately. So here I decided these thresholds that you can explore here, and I will show you my source in a moment. So here in the EOS Data Analytics website, we have some information about different vegetation indexes. And in this case, we have the normalized difference moisture index. And here you can read a bit of the description about this index. Here we have the formula, and depending on which satellite imagery we are using, the bands are different. And here we have what I'm interested in, which is the interpretation of the values. And if I make this smaller, we can compare it with what I did, which was to use the values that goes from -inf to -0.2. So I put everything of these four classes into just one class, which I called low or very low canopy cover dry or very low canopy cover wet, which is basically the name of this one. And this is because we almost don't have values that goes beyond minus zero point 0.4. So I think it was fair to put everything together into one class. Then from minus zero point 0.2 to 0, we have the mid-low canopy cover, high white water stress, or low canopy cover, low water stress. So basically this index, what it will measure is depending if we have high, low, mid canopy cover, the water stress will be different for the same values. What I mean is that here we have the same range of values, but if we have mid or low canopy cover, these values will mean that the water stress is high. But in the case that inside these values we have low canopy cover, the water stress will be low. So that's how we interpret this index. And then we have the next class, which goes from zero point 0.2 to zero point 0.4. And finally, we have the last class, which goes from zero point 0.4 to inf. So I put everything from these three classes together, which is basically no water stress. Because here we have high canopy cover, no water stress, very high canopy cover, no water stress, and so on. So I think it was also fair to put everything together into one class. And as you see, the maximum value is 0.62, so we don't have almost anything in these two classes. Alright, so once we understood this, I will run this line of code, which is basically creating a matrix for the transformation. So here we say from minus inf to minus zero point 0.2 will be converted to 1, from minus zero point 0.2 to 0 will be converted to 2, and so on. And we can apply this classify function to classify the values following this matrix, and then we convert it to a categorical variable. So I will execute it, and I will print it again in the console once it's finished. It should take a couple of seconds. And now we see that the minimum value is 1 and the maximum value is 5. And if we use this function levels to the levels of this layer, we will see this list. So it's a list because we see these brackets and this one. So I can access the list by saying again these levels and brackets 1. So now we are inside the list, and here we have a data frame, and I want to change the levels of this column. So we want to change them for this vector. So when we create the visualization, we will see these values instead of 1, 2, 3, 4, and 5. So I will execute it. And now if I call the levels of this layer, we see that we change these values right here, which are the labels. So now once we've done this, we can create the visualization. And this visualization is not very complex. Here I added the first geomspat raster layer with the NDMI. So if I execute only this part of the code, we will just see a very basic plot of this layer. So there we have it. Then with the scale field whitebox underscore D, and we need to use underscore D because this is for discrete values, and this is a discrete variable, it's not continuous anymore. And here I'm using a different palette, which is one that goes from blue through yellow and red, and I'm using the direction -1 to reverse this palette. So I will execute this part so we see how it looks. And there we have it. So now the next step, I'm moving the guides, and the guides will control the legend. So what I'm doing is to put the legend inside the plot, not here, inside, and I'm removing the title. So I will execute only this part of the code, so we'll see what happened. It should put the legend in exactly the middle, but later we will move it to a different place. So the next step is just this theme void to eliminate everything from the background. So it looks like this, and I also changed the base family and the base size of of the text. And then with this theme function, I add other customizations, like the legend position inside is when we have this position inside, where exactly do we want the legend. So I set 30% of the x-axis and 8% of the y-axis. And then here some different units to change the size of the different elements of the legend. And don't worry if it looks very small now, because later it will look better. So I will execute this, so we save our plot to this variable. And then we will do more or less the same for the NDVI. In this case, I'm using this scale fill whitebox, but in this case _C, because here we have continuous values, not discrete values. I'm using a different palette called muted. So if I execute only this part, we have this result. And here for the legend, I have some slightly different code. So I want it also inside. I want the title of NDVI. The title should be at the top of the legend. The title should be justified in the center. And the direction of the legend should be horizontal and not vertical as it is there. And there we have it. But now it looks horrible, so we need also some customization, which is inside this theme function, which is basically moving it. So again, 30% of the x-axis and 80% of the y-axis, and other different arguments to modify the size. So I will execute it. And now the last part of this script is to put the plots together. So we are summing them, and when we sum them this is with the patchwork package. So if it's not loaded, this package, this sum won't work. It will throw an error. So there we have our two maps. And then with this plot annotation function, which is also from the patchwork package, I'm adding the title, subtitle, the caption, and I'm applying something to the full plot. So I'm changing some format from the plot title that we are adding, like the family. I want it bold, the line height. I want also some margin and justified in the center. And for the plot subtitle, I want it justified in the center. And the plot caption, I want it also justified to the center, and also changing the family to robot. And this is how it looks, our final map. But now we need to export it. So here I save it with this name. I gave it these dimensions after experimenting a little bit. So I will execute it. Alright, so this is our final map, and as you can see now, the font size doesn't look so small anymore, and we can read well the text. So I think it looks cool in the end. And here we can also evaluate, like the month before in average, we don't see a very high drop of the NDVI values here, but we needed also to compare it how it should be compare it maybe with other years or with the months before, because these areas are very dense forest, and maybe these values between 0.25 to 0.50, maybe they are quite low for this type of forest. And here we can see that the moisture index, there are some areas that are this blue, which is in mid-high canopy cover, which is the forest that we have there. It says that the water stress is high, or if the canopy cover is average, the water stress is low. But these yellow areas, which are also areas that have burned, and as you can see, like they are more or less mixed, we have also areas where average canopy cover have also high water stress. So we can see that in general, most of the island had a high water stress the month before the wildfire. So this was everything for this tutorial. I hope you enjoyed it and that you also learned a lot with it. And if you did, please leave a like, and if you would like to see more of this content, you can also subscribe, because I will try to create one of these maps or do a different analysis in R each 2 weeks. So see you then.